We are very happy to have Marija from Barcelona, and she will tell us about the strong cosmic censorship in the BTZ black hole. Please start.
Thank you. Thank you for giving me the opportunity to talk. I hope you're all staying safe. As you mentioned, I will be talking about strong cosmic censorship in the BTZ black hole, which is work that I done with Roberto in February of this year. And so here is the outline of the talk. I will start by introducing what the strong cosmic censorship is and some of the basic notions that go into the understanding of the conjecture. Then I will try to summarize what is the current status of the formulation of the strong cosmic censorship. It has a long history, and I don't think we're done yet, but I'll try to summarize it in a couple of slides. Afterwards, I will explain why the BTZ black hole is so special. And then I will explain what is the idea that Roberto had, that we developed, the setup in which we analyze the BTZ black hole, and then I will conclude. So to begin with something that we've known for some time now, which is the singularity theorems due to now a couple of authors, Penrose and Hawking and Wall most recently, where they stated in these various singularity theorems that under certain reasonable initial conditions, we must encounter a singularity within black holes, or in other words, singularities or quantum gravity regions are inevitable in physically reasonable spacetimes. And now, just because singularities are inevitable inside of the black holes, that does not mean that we can probe them easily, or even that we can probe them at all. And so this is what the cosmic censorship is all about, being able to probe the singularities. And now you can pose this question in two ways, depending on the observer that you are interested in. And so if you want to talk about the asymptotic observer, you will be talking about the weak notion of the cosmic censorship, which basically would say, in an intuitive way, that no asymptotic observers can ever see a naked singularity. So a naked singularity will be a singularity that's not behind the black hole horizon. And so in a more mathematical way, cosmic censorship would say that the null infinity has to be complete. And now there is another way that you can pose this question of cosmic censorship, which is with respect to the infalling observer. And so this is the statement of the strong cosmic censorship, saying that no infalling observers can ever see a naked singularity or probe a singularity within black holes. And in this talk, I will focus only on the strong cosmic censorship. And just to be clear, strong cosmic censorship was conjectured for black holes. It deals with infalling observers. And most interesting examples as a testing ground for strong cosmic censorship are the Kerr black hole and the Reissner-Nordstrom black hole. However, both black holes exhibit similar behavior, and so they will be placed on an equal footing in this talk. But I will talk mostly about the Reissner-Nordstrom black hole as a simpler cousin of the Kerr black hole. However, before I dig into the actual Reissner-Nordstrom setting, I will introduce some important notions that one needs to have in order to understand what cosmic censorship is about. So we go to our favorite textbook, and here we have two spacetimes presented. This is the Minkowski and the Schwarzschild black hole. And I would like to introduce the notion of a domain of dependence. And so in general relativity, the values of fields in space-time are uniquely determined by the values at an initial time slice. And this is within the domain of dependence of this initial data surface. So the initial data surface is the sigma. This is where we put our data in terms of the induced metric, the extrinsic curvature. And then we can use that data to evolve in the future or in the past. And the fields and the values of the fields will be uniquely determined only in this green region that is shaded here, which represents the domain of dependence associated to this sigma slice. In the Schwarzschild black hole, a similar situation happens. So the domain of dependence is this whole green region here. You might have thought that there would be something wrong because of the singularity here, but the spacetime cannot be extended beyond the singularity, and so the fields that you specify on this slice really are determined within this whole spacetime. A more mathematical way of saying this is that, for example, the future domain of dependence is consistent of a set of all points whose causal curves will intersect the initial data surface sigma only once. And so you see that this is just an example of a point whose causal curve intersects this sigma surface. And you can easily convince yourself that wherever you pick a point in this spacetime within this green region, all of its causal curves will intersect sigma only once. Now we can look at a slightly different example. This is now a Minkowski spacetime with one point removed. And so it may occur that spacetime extends beyond the domain of dependence. Like I said, this is Minkowski, but so it would naturally go form a little hat here. But since we have removed the one point, we have changed the domain of dependence. And in this case, the domain of dependence is, again, everything shaded in green. And these blue lines are the boundary of the domain of dependence, and this is called the Cauchy horizon. So Cauchy horizon, which I will call H plus of sigma, so associated to this initial surface sigma. And now, just to be clear, if I was to pick a point somewhere in this 2B Minkowski region, then there would exist some causal curves that would end up in this removed point, or just like leak out. So they wouldn't be able to reach the sigma surface, and so they wouldn't intersect it, and therefore they're not a part of the future domain of dependence. Okay, so these were the basic notions. Now we can dive into the Reissner-Nordstrom black hole. Here I have drawn just the maximally extended Reissner-Nordstrom solution. Almost, it has in both directions infinite pattern of these. But what we're interested here is, again, some Cauchy surface sigma and the domain of dependence associated with it. And as you see, the green region is the one that we have a unique determination of field values, but there exists this gray region beyond the Cauchy horizon, which is obtained not by the evolution of field equations, but by analytic continuation. It's a completely new universe. It cannot be determined from our initial data. And so just to emphasize, fields are uniquely determined in this green region, but they're not in the gray one. And this causes a problem for classical physics and determinism, because usually you would be given some initial data, you have your equations of motion, and in principle, you will be able, with this data and equations of motion, we'll be able to determine everything that happens in the future. But here we see that at some point in time, you would simply cross this Cauchy horizon and you wouldn't be able to say what happens here, given just the initial data on the surface. In other words, this would indicate a failure of determinism within the spacetime. Now, this is a very big problem. There is another problem, but just before I move on, I just want to emphasize that whenever I talk about Cauchy horizons from now on, I will always refer to the ones inside Reissner-Nordstrom and Kerr black holes, so not any other possible Cauchy horizons in any other spacetimes. So what is the other problem that we might encounter? We might encounter it from a holographic point of view. And here I have semi-badly drawn a Reissner-Nordstrom anti-de Sitter spacetime with the CFT associated to it. So here we have a couple of CFTs determining everything inside. Sorry, so everything inside is determined from the initial slice in this green region as before. The gray region is the new universe. And here we have a different problem because there exists such a thing called the no transmission principle that was discussed, to my knowledge, first by Engelhardt and Horowitz in 2015. And this no transmission principle basically says that two quantum field theories, which are independent, cannot send signals to one another. But here we see that in this space-time, naively, we would be able to send a signal from one another from this one region here, the green region, to the other CFT that's associated to the new universe. So this CFT is associated to one ADS, asymptotic ADS patch, and this one is associated to the other one. So there would be two independent QFTs. What this would mean, if we were able to send these signals, is that our CFT would not encompass the whole bulk. The whole bulk then would be encompassed by two or maybe infinite CFTs that will exist associated to each asymptotic region. And so we would not have the full UV completion of the bulk theory, which is not something that holography stands for. Well, in holography, we would expect that the CFT would be the UV completion. And so we see that if we were to allow such propagation of signals or even fields to go in this gray region, we would have various problems. However, we have been discussing so far the mathematical structure of this Reissner-Nordstrom black hole, and one might wonder what would happen if we were to send an actual observer to examine what happens at the inner horizon. And so this question is exactly what prompted Penrose in 1973 to argue that if you were to take fields and evolve them in the space-time, dynamical fields, that those fields, when they reach the Cauchy horizon, they would have a catastrophic behavior. And hence, this would be the first formulation of the strong cosmic censorship. Now, we can go and review what Penrose's original argument is, at least as a little sketch. So let's start with the usual Alice and Bob, where Alice travels to the future infinity, and it takes her infinite proper time, while Bob falls into the black hole, and he reaches the Cauchy horizon in a finite amount of time, finite proper time. And now Alice misses Bob, of course, and she sends him periodic messages according to her time that she misses him. And these arrive more and more frequently at Bob according to his time as he goes on. So here are the little signals being more and more compressed as they reach the Cauchy horizon. Similarly, since this is just an analogy with two observers, if you were to take the actual fields and evolve them in the space-time, you would see that they would oscillate, if they oscillate very moderately near the future infinity, they would oscillate very rapidly near the Cauchy horizon for the same reason of this squeezing of signals, so to say. And this whole effect is called the blue shift effect. And indeed, it would be the infinite blue shift effect as one approaches the Cauchy horizon. The Cauchy horizon is indicated here. So with this little thought experiment, we can now formulate the strong cosmic censorship in a slightly more precise manner, which is to say that the Cauchy horizon actually doesn't exist in practice. Or in other words, any slightest perturbation of the metric or the matter fields will become sufficiently singular such that the solutions couldn't be extended across the Cauchy horizon. And so if the strong cosmic censorship would hold, the Cauchy horizon will be converted into the final singularity. There wouldn't be the time-like singularity as before. And so we could not extend above that singularity. It's just like in the case of the Schwarzschild black hole. And in that case, determinism will hold. So it's definitely something that we want to have. However, formulating the strong cosmic censorship precise enough turned out to be really a subtle issue. And this was something that over the years, many people have attempted to formulate, to come to an actual final formulation that would be physically reasonable and correct and also interesting enough. And so a plethora of results has been obtained. I can only say some good references for small reviews, if you will, and those would be the introduction sections of Diaz Real Santos paper from 2 years ago, where they mostly discuss the classical approach to this problem. And then the one paper by Hollands-Wald-Zahn from December last year, where they take a more quantum perspective. Now, if you don't feel like reading, I would suggest that you go to the KITP website and find a talk by Stefan Hollands that he gave at the conference that was occurring in KITP these 3 months. He gave a really nice talk where he went into more details of the construction with Wald-Zahn and in general more details of the calculations being done. Here, I will only give a very short review of these reviews, and hence I will miss out many, many things, but I would just like to give an intuition for how these things evolve. So Penrose-like arguments, like the one with the infinite blue shift, show us that the spacetime is not C2 extendable, which translates into curvature invariance blowing up at the Cauchy horizon. C2 here refers to the fact that the curvature is conducted out of two derivatives of the metric, and so the metric has to be C2 at least differentiable. And what Penrose-like arguments show is that a curvature blows up. But just because the curvature blows up at the horizon, that doesn't mean that you as an observer while crossing it has to be destroyed by tidal forces. You are described by geodesics, and geodesics don't require the metric to be C2, they're required to be at most C1. And moreover, it was proven that the metric is actually continuous across the horizon. So without any reference to the derivatives, you can completely extend the metric across the Cauchy horizon. So this looks bad, but
Marija,
remember—
can I ask a question?
Yeah, sure.
When you just said it was proven that the metric is extendable across the horizon, this is for which case?
This is for the Reissner-Nordstrom zero cosmological constant case, I would say.
With no perturbation?
These are the vacuum equations, yeah. I would say—
I guess I'm confused because I would have thought that the analytic continuation is that proof and that it's better than C0.
Yeah, I guess you can say that. Here I'm trying to just put a little, as you will, a little hierarchy with what is important when you speak about differentiability. So is it C0, is it C2, is which C to follow? But you could have said that analytic continuation would be just enough. I would say that I agree. But of course, I will have to refer you to these mathematical papers because they have gone in much more detail, and I have not looked at those.
I'm trying to understand whether C0 is sort of the mark you're laying down as the minimum acceptable sort of property of the metric, or just something that happens to be true in some example.
I would say that this is something that happens in all examples. Unless if you can come up with something weird. But I would say this should be true everywhere.
But in the example where Alice keeps sending messages, it would not be true, right?
Well, Alice keeps sending messages is a fact of the, as I said, the curvature invariant blowing up. This doesn't require you to actually talk about the metric itself.
So is the statement that even then the metric is extendable in this way?
Yeah.
Oh, okay.
Yeah, so this is why I was talking about a hierarchy. Like C2 is something like above. C0 is the smallest thing that you can have, and it was proven, and I should check this, exactly which examples, but I would say in all physically reasonable examples.
I mean, it's sort of hard to violate C0, right? Because,
yeah.
I mean, if you violate C0, you no longer have a connected manifold, right?
Right. So I would say that even with that, you can argue that just by having analytic extension will be enough to say that.
Analytic is C infinity, but I'm saying even if I'm sending in shock waves that make the curvature invariance blow up, it seems sort of hard in general to cook up an example that breaks C0.
Yeah,
so I just want to make sure I understand. So in the case of, let's say, the ordinary space-like singularity inside a Schwarzschild black hole, we don't think we can extend this C0 or otherwise, right? But you're saying that in the examples where you perturb a Reissner-Nordstrom black hole, you always expect to be able to extend it at least C0?
I would say yes, but I would have to check now for this particular point. Maybe I can get back to you on Thursday with this.
Okay.
What I wanted to make with this point is exactly what Grant said. Like, it's hard to make the metric not C0 across the horizon. Schwarzschild is different. Here we're talking about the inner horizon of the black hole. But maybe what I'm about to say next will be also help. Because we don't, in the end, we don't care about the metric being extendable in a C0 manner. What you do care about is that you can extend the metric, if your observers can actually cross the horizon, which doesn't talk about the metric being C0, that talks about a different condition. And so for an observer to cross the Cauchy horizon, what this means is actually involving the matter fields with equations of motion and analyzing the crossover over the Cauchy horizon. And so you might have thought that equations of motion would require you to have C2 from the metric and matter fields, which we've shown that they're enough to have a singular Cauchy horizon. But in fact, you can have some solutions that don't require C2, but are something less. For example, shock waves, as I think Grant mentioned at some point. So shock waves and fluids and such solutions are called weak solutions. And the way I would just give some intuition for them is just smearing the fields and then evolving them across the horizon. A more mathematical way of saying this is that the weak solutions are the ones that have locally square integrable Christodoulou symbols. And so with this notion in mind, we can come to the Christodoulou formulation, which is that maximal Cauchy development, so as far as we can go with our equations of motion, is generically inextendable in these black holes with locally square integrable Christodoulou symbols. So this means that your metric is C0, but if you don't have locally square integrable Christodoulou symbols, then you cannot extend over. So is this clear then? Raphael?
Sorry, I had trouble unmuting. Yes, thank you.
Okay. Good. So now we have come to the formulation that, at least to my knowledge, I have seen is the latest formulation. And this was proven. This Christodoulou formulation was proven for Reissner-Nordstrom and Kerr black holes in the asymptotically flat spacetimes. Now you might wonder what will happen if we were to turn on the cosmological constant, either way for ADS or de Sitter spacetimes. And for the ADS spacetime, the formulation is still valid in most cases, and this is something that I will come back to later. But for the positive cosmological constant, we have a competing redshift effect coming from the fact that we have an expanding universe on the outside, which would dilute the oscillations of the matter fields and hence not make them oscillate so rapidly near the horizon, so as to make the horizon so singular. And indeed, this was a problem, especially because positive cosmological constant and Kerr black holes are something that we expect to be fairly physical. So now, to see a little bit more clearly what happens at the horizon, it is instructive to look at the form of the stress tensor of the scalar field as a test field as we approach the Cauchy horizon. And so numerous papers have shown that the stress tensor will have this form. This little v here is supposed to be the big V, but I couldn't make it be a big V. I don't know why. Big V as in the Kruskal coordinate. So this would be direction transfers to the Cauchy horizon. And so the stress tensor of the scalar field would behave in this manner when we approach the Cauchy horizon, where this d is some constant that depends on the solution. And beta is a parameter that's not a temperature, but it depends on the black hole parameters. It's a combination of something called the spectral gap, which is a property of quasi-normal modes, and the surface gravity of the Cauchy horizon. It's something that depends on black hole parameters in any case. For beta equal to 0, we get the same solution as for the asymptotically flat case, and therefore we have a singular stress tensor at the Cauchy horizon. In that case, the stress tensor we go with 1 over v squared, which is singular enough for our Christodoulou formulation to hold. However, specifically Diaz, Real, and Santos, and others have found that there exist physical black hole parameters for which beta would be greater than 1/2, in which case this wouldn't be enough, not singular enough to stop Bob from crossing the horizon. Actually, it would allow him to cross through the Cauchy horizon. And so this is obviously a problem. However, all of these results were obtained in the classical regime.
Maria?
Yes.
Can you comment on what is an example of a, so this is a Reissner-Nordstrom de Sitter solution that exhibits this, and could you say what are the parameters in terms of mass and charge or whatever you, I mean, so how does this beta greater than 1/2 translate into what kind of black hole in de Sitter space this is?
So this was done, I think, just for near extremal black holes for Reissner-Nordstrom. Beta is given as something called alpha over kappa. Kappa would be the surface gravity of the Cauchy horizon. And alpha is something associated to the quasi-normal modes, which you have to extract from the perturbations of the horizon, and it's a hard calculation that you have to do. So this is the way, if that's what you were looking for the exact form of beta. In 4 dimensions. So this is all in 4 dimensions. In 2 dimensions, beta, I think, is just the ratio between the cosmological horizon surface gravity and the Cauchy horizon surface gravity.
Okay, so I guess this means that the black
this.
holes have to be pretty large compared to, they shouldn't be very much smaller than the de Sitter horizon radius, which makes sense. Yeah, thank you.
What I said is that if we include quantum effects, one might wonder if the story would be changed. And this is exactly what was done in this paper by Hollands-Wald-Zahn. This is where I mostly stopped. So what they did specifically is that they analyzed the stress tensor of a real linear Klein-Gordon field near the Cauchy horizon inside the Reissner-Nordstrom de Sitter black hole. But their results are they are general enough that they would apply to the current Newman case as well. Now, before I move on to explaining a little bit more what Hollands-Wald-Zahn did, I just want to mention another paper by Papadodimos, Raj, and Shrivastava, where they conducted a simple test to determine whether the horizon is smooth, and I encourage you to read that paper. Basically, what they were looking at was the correlations between the modes across the horizon. In other words, saying if the entanglement structure across the horizon is correct, if the modes have the correct entanglement structure. And so their test could determine if the horizon is smooth or not, or if the inner horizon can be smooth, and if that's compatible with the outer horizon also being smooth. But their test, even though it's simpler than computing the full renormalized stress tensor, it has a small fault, which is to say that the test only gives necessary results, but it's not sufficient. So if you would see with the test that the horizon is not regular, that will be enough to say that it's not regular. But if the test tells you that the horizon is regular, that still doesn't mean that that's the final story, because it's not a sufficient test. However, I still encourage you to read the paper. Now, I will discuss a little bit more Hollands-Wald-Zahn. So if you remember, with our initial data surface, we had to put some regular initial data and then evolve that regular initial data with our equations of motions, because it doesn't make sense to start with something that's not smooth from the beginning. And the analog of that for the quantum fields is something called the Hadamard condition, which is basically just saying that the UV structure of these states should be the same as in Minkowski. So again, the states that we begin with should not be more singular than the ones in Minkowski, because then they wouldn't be a good test of whether or not stuff blows up at the Cauchy horizon. And so using such states within the semi-classical gravity regime, they managed to show that the stress tensor actually diverges as you approach the Cauchy horizon, and not just in any way, but in a quite universal way. So here, the little v's are against big v's. Psi is the state that we're using here with the Hadamard structure. And the stress tensor goes as some constant over v squared. And there are some subleading terms. So there is no effect of something like the beta here, lowering the divergence of the stress tensor. It just goes as 1 over v squared.
Can I ask a question?
Yes.
Just so I understand the, so we're looking now at these beta greater than 1/2 solutions in de Sitter space, and
okay.
we're perturbing them in some way so that we can, because we're not interested in this very special one where it's unperturbed, but we're only interested in whether the spacetime is extendable for these perturbed ones. And now we're studying the stress tensor on that perturbed solution. So basically we have enough control over what the solution looks like near the inner horizon to do this.
What you know is how the one component of the stress tensor will look like.
But you have an exact solution for the metric?
You could do such a thing. I don't think this is what they have done. This is something that was done before, in the 90s or something like that, where they like had the specific Vaidia-like solutions. But here they were analyzing the behavior of the stress tensor just near the horizon. But I will have to refer you to they're fairly long and complicated, to the Hollands-Wald-Zahn paper.
But I'm confused. How could you possibly compute the stress tensor if you don't know the metric?
I mean, you know the metric.
So you know the metric for this perturbed solution.
So the way I understood it is that you start with a metric and use that metric in order to solve the equation of motion for the stress tensor, right? And so
yeah.
That stress tensor is the one that you are using. And then you would have
the
to...
metric...
Is the unperturbed one, or?
It's the unperturbed one, I would say.
Oh, okay.
If somebody can correct me if they know a little bit more, but I would say that like you start with a metric and then you use that metric and for your equations for the quantum field theory stress tensor. And then when you obtain that stress tensor is the one that you're looking at.
Oh, I see, that makes sense. So it's just a statement that if you just put the thing on a fixed background, which is the unperturbed metric, the stress tensor blows up, and so the perturbed metric would be crazy.
Yeah.
Okay, thank you.
So there's no back reaction. Thank you. Right, and you can see here that this behavior, this divergent behavior, is entirely due to quantum effects because this constant c goes as the order h bar. Now, what's interesting is that this constant c depends on black hole parameters, but it doesn't depend on the state, which is different than the case in the classical case where we would have dependence on what our initial data is and how regular it is and what happens with the initial data. But here, the leading divergence is completely independent of that, and it's only associated to it only depends on the black hole parameters themselves. And just to say, in these subleading terms, we will see a structure similar to that as this classical stress tensor, so 1 over v squared minus 2 beta. But since 2 beta can make this divergence smaller, then I'll just put it here in the subleading terms.
Is there a genericity assumption about the state? So, or are you saying this even holds for the Hartle-Hawking state?
What they obtained is so the 1 over v squared structure is something that is what you can obtain just from symmetry arguments. The point is if this constant c is going to be 0 or not, and that is something that depends on the black hole parameters. So this constant c can be 0 and some measures at 0 set of parameters, some very small fine-tuned set of parameters, but generically it's not 0. So that you would always have this divergence. And this is, I think that they did it in like the Unruh state. straight state-like structure. Does that make sense?
Yeah, thank you.
Okay. So as I mentioned before, they derived this result for the Reissner-Nordstrom de Sitter black hole, but the method should apply to the very similar Kerr-Newman case. And also we saw that divergence will always be there, provided just that the constant is not zero. And as I said, this is true generically. So this is the only generic part of this discussion. And if the stress tensor diverges at the Cauchy horizon in the manner that we have seen, so 1 over v squared, then we cannot extend even the weak solutions. And so the strong cosmic censorship will hold, or in other words, poor Bob is bound to fry. Now, why am I giving this talk? It so happens that for the BTZ black hole, the constant C is equal to 0 due to some various cancellations that are in the long calculation that Hollands-Wald-Zahn did. And this, I would say, can be explained by the highly symmetric nature of the BTZ black hole. It's in 3 dimensions, it's a quotient of ABS. So it's a highly symmetric solution of Einstein's equation. However, as you mentioned, the Hollands-Wald-Zahn paper worked with the first order correction. So you could wonder that additional corrections could make this constant not to be equal to 0. And just to mention, the Papadomimas, Raju, and Srivastava paper also obtained that the BTZ black hole passes their test of regularity. So for them, they also see that the Cauchy horizon is regular. However, as I mentioned, their test is a necessary one, but not sufficient. Okay, so in order to see how the additional corrections would change this calculation, one would need to do a very hard job of computing at the same time, if you will, the Einstein's equations with the coupled matter field equations. But we will skip all of the hard calculations and using holography, argue that corrections do save the strong cosmic censorship. Now, in order to do so, I will just explain in a very basic manner what is the holographic setup that we're using. All of the details can be found in the original paper by Paran, Horowitz, and Myers in the 90s. But here I will just say that what is the point of their model, which is that they had a ADS4 solution, which is some specific metric called the C metric with rotation. It really doesn't matter what it looks like. And that will be dual to the BTZ black hole coupled to a CFT. The C metric with rotation describes a black hole that follows an accelerating trajectory in 4 dimensions. And slicing through that black hole, basically, you arrive at our setup where we have a BTZ black hole on a brane coupled to a CFT. So this is where we are. And because the BTZ black hole is coupled to a CFT, we don't have exactly the BTZ metric. We have one that is corrected by quantum effects or bulk effects because it's on a brane. And so here I'm just showing how the metric looks like for this quantum corrected BTZ metric. All the corrections are encoded in this alpha parameter here. It depends on the black hole parameters. And so if you were to put alpha to 0, you would see that we arrive to the BTZ metric itself. And this metric is sourced by a stress tensor that it's irrelevant how it looks like, but I wanted just to show that it depends solely on alpha and that this stress tensor is regular at the inner horizon. It only has a divergence at the singularity r equals 0. Now, the paper from the 90s didn't quite call these corrections quantum corrections. This was understood later on in a different paper by Paran, Fabri, and Kaloper, which explained most of the setup and how you should think about these black holes on branes. But here I will just summarize what is the result of their paper, which is to say that these brane-induced modifications of the BTZ are viewed as quantum corrections coming from a CFT. In other words, this construction gives us only a leading order in 1 over n expansion geometry, leading order in 1 over n of the CFT. So when the bulk dual is purely classical. However, you can already see that these corrections are enough to make the BTZ black hole lose its highly symmetric character. It's now a different metric. It has this alpha component, so it's no longer as symmetric as it was before. And so by including quantum corrections, now repeating the procedure of, for example, Hollands-Wald-Zahn, you might wonder if the story would be different. In other words, at finite order in n, you should include these quantum corrections in the bulk. And so this, again, sounds very bad, very hard to do, but we can apply a holographic trick within this setup now. So let's go back to the 4D setting. The black hole that is described by the C metric on an accelerating trajectory actually has a structure that is very similar to the Kerr black hole. And you can check that the metric on the brane that I showed previously is the same as the equatorial section of Kerr ADS. And this 3D black hole on the brane therefore inherits a singularity and the inner and outer horizons coming from the Kerr-like black hole in the bulk. So the singularity would be R equals 0 and R equals R plus and minus on the brane. However, you recall that Hollands-Wald-Zahn obtained a result that is applicable to Kerr-like black holes. They did it for the Reissner-Nordstrom case, but they said that the arguments or their methods are general enough to apply for Kerr black holes as well. And so this Kerr black hole in the bulk should have a singular Cauchy horizon if we were to repeat the analysis that they did. But since this black hole in the bulk shares the inner horizon with the black hole on the boundary, on the brane, then the same conclusion will be true for the BTZ black hole as well. And so in one sentence, the BTZ black hole should obey the strong cosmic censorship when we include these additional quantum effects. I will just conclude now. So we see that quantum effects can significantly change the story told by the classical theory. And an important example of this is the stability of inner horizons. And when the calculation gets too hard, we can apply holography as usual. And by using holography, we can argue for the validity of strong cosmic censorship in the BTZ black hole. So if you didn't pay any attention in this talk, the main lesson is that you shouldn't underestimate the importance of quantum corrections, especially not in highly symmetric spacetimes. Just to have a little coming up slide, I would like to mention work that is coming up. So, as I said before, we have seen enormous development in the research of semi-classical geometry. And with this paper and many others, we have seen increasing evidence that quantum effects save the strong cosmic censorship in general, so that they should be valid for all black holes that have Cauchy horizons inside. However, I did not talk about another cosmic censorship. There is also the issue of the weak cosmic censorship. And weak cosmic censorship is fairly important because it goes into many theorems from classical general relativity and also semi-classical general relativity. It's one of the key assumptions. But unlike the strong cosmic censorship, which is fortified by quantum effects, weak cosmic censorship is almost definitely violated by quantum effects. For example, at the end point of an evaporating black hole, you will have a naked singularity, which would constitute a violation of the weak cosmic censorship. And so one would like to have a generalization of this notion, and generalization would come by including quantum effects into the cosmic censorship to have a quantum cosmic censorship conjecture. So this is something that we have been working on that I guess Raphael will talk about at some point. But this is it. So thank you.
Marija. Is there any questions?
I put out this picture so that people would ask me, what is it? I can just tell you, this is a picture taken from Lake Berryessa in Napa Valley, and it's amazing. This looks like a black hole, and I definitely advise you to go there and visit it once this corona has passed.
I guess I have a comment and a question. Just because it wasn't on your slide, I should say that this joint work also involves Netta Engelhardt. And the question is, you said near the very end that quantum effects sort of help the strong cosmic censorship, and in particular that weak cosmic censorship is violated at the endpoint of black hole evaporation. But at least I think if we define strong cosmic censorship as a failure of global hyperbolicity, then surely it too would be violated there, right?
That is correct. That's why I wanted to emphasize that we were talking about Cauchy horizons inside black holes always. So it's not to confuse as any other Cauchy horizons that might emerge from, for example, evaporating black hole. And at the end, you would have a Cauchy horizon forming there, and you wouldn't expect it to go under the same destabilization process as the one inside. So what I wanted to say is that inner horizons should be unstable and be converted into a final singularity. That would be somehow the way I would formulate the strong cosmic censorship framing. Because I agree, global hyperbolicity would be violated in general. Thank you.
So Maria, I have a question. Another way we could formulate sort of what we mean by cosmic censorship is that an external observer shouldn't be able to access regions of arbitrarily high curvature, even arbitrarily high but finite curvature. This is sort of how Gary Horowitz likes to talk about cosmic censorship in the context of the things he's been saying about the weak gravity conjecture. But I was wondering, as I recall, for dilatonic Reissner-Nordstrom black holes, so charge plus a dilaton, there, if you take the extremal limit, the area of the two surface goes to 0. So the singularity hits the horizon. It's not outside the horizon, but nonetheless, for extremal dilatonic black holes, the external observer could, throw particles near the horizon and access arbitrarily high curvatures.
Oh, is that a problem? Horizon?
Yes, the event horizon for the extremal charged dilatonic black hole has area equal to 0.
Uh-huh. I really
so that seems, even though it's not formally a problem from the point of view of cosmic censorship, because the singularity is not outside a horizon, it sort of morally seems like a problem. So it would be nice to have some version of cosmic censorship that kind of gets at that intuition. I was just wondering if you had any
that would just disallow any observers to probe any sort of quantum gravity regions.
Yeah, right.
Right. Yeah, I mean, this is what I would say is reasonable, but I did not know about this example. Thank you for this. Maybe you can send me a reference, but at least in these very, at least in these very generic examples of just Reissner-Nordstrom,
Yeah. Right. It would be cool if like a mass somehow forbidden by some souped up version of cosmic censorship.
Right. I agree.
Can I ask a question about that? Yeah. I mean, it seems to me that if the area is 0, I'm not familiar with these solutions off the top of my head, but if you say the area of the event horizon is 0, that seems to me very similar to the case of the endpoint of black hole evaporation for an ordinary black hole, where we would propose, so for example, the way that we propose dealing with this sort of situation is to say that small violations of cosmic censorship have to be acceptable if they involve regions that, roughly speaking, can be surrounded with very small areas, so there's little quantum information coming out of them. I don't know if that would encompass the kind of solution that you have in mind.
It might. One concern I would have is that, the endpoint of black hole evolution is it takes place over a finite duration in time. So even if we kind of violate what we mean by cosmic censorship, it's only briefly. Whereas, these extremal dilatonic charge solutions can kind of sit around and hang around forever. And that
That's a
seems
good point.
like more
That
of a
sounds
problem.
like a difference, yeah.
And this is not excluded by some swampland conditions?
Yeah, it's not, yeah.
No,
that's
well, I mean, if you have particles that are highly charged and that you know, interact with the dilaton, then sure, these objects are unstable in the same way that extreme Reissner-Nordstrom is unstable. But just as, I mean, we still talk about extreme Reissner-Nordstrom as a, or nearly extreme Reissner-Nordstrom as a solution we're allowed to think about. So I could deform away from extremality slightly and make these things arbitrarily long-lived, even while formally satisfying the swampland criteria.
Yeah, it will be
the magnetic version of what I'm talking about is called the CGHS black hole.
Wait, I thought those evaporate.
Right.
There's an extremal version that doesn't, I think.
Okay, so we should maybe, I would be very interested in learning.
Yeah, I'll post a link in. Maria, are you on the BCP Slack or?
Yeah, I am.
Okay, I'll post this there.
Okay, but this is just in 2 dimensions, right? If you said CGH, this is a 2-dimensional.
No, oh, sorry, I may have given the wrong letters. I'll send you the link.
Okay, thank you.
Other questions? All right, if not, then let's thank Maria again virtually. And
thank you.